Okay, hello everyone. My name is Philip, and I'm presenting my presentation for my bachelor thesis, which I have finished a year ago, and I hope you enjoy it. So, here we begin. Once upon a time in a kingdom far, far away, it was me who uptook the perilous journey through blistering cold and scorching desert, calculating for many days and nights, risking sleep and sanity to reach the dragon's keep. For I was the bravest and most handsome in the land. And it was destiny that my work would break the dreaded curse of fame. And so, here is the agenda of this presentation and my thesis. We will go through what was the initial idea and what was the challenges of the thesis process compared to what it could have been. Then the problem of the software LS Dyna, which some of you might have heard of, but we'll get to it. Then there will be results of my modeled specimens and some conclusions and recommendations for continued research in HAMK, and then practical applications and labor market links, but that was basically an insert for my thesis because it just had to be in there. But maybe you have some ideas about that, and hopefully we'll have some times to answer your questions if you'll have any. So this is what I have got. The results of previous theses in the series, which there were 4 of, and it included a test of high-strength steel and high-strength steel welds, particularly strength 700, a product of Rookie. As you might know, the high-strength steel problem is that it's extremely strong, but when you weld it and the heat input is too high, the properties of steel weaken dramatically, and the joint becomes the most critical part of the structure, and the brittle failure might occur there, which we usually don't want to have. So this is the input that I got, along with 4 physicists filled with information about them. And this is what I have made, a modeled specimen of the test. On the left, you can see the initial idea and division of material zones. So the red being strength and the base material, for which I had all the properties. Then the weld material, for which I had some of the properties and had to assume some of them. And the heat affected zones, the main problem and research goal of this thesis, because properties for it is basically undefined and a lot of assumptions has to be made. I ended up having 3 main ideas how to model it and tested all of them. And on the right, you see part of the result animation of the calculation of this model, which shows the fault line and the main plastic strain areas. Okay, here we go. So the goal of this thesis was to create a realistic model of the experiments performed by Jimmy Giraldo a year before my thesis, so in 2018, and leave as many explanations and instructions for people doing further theses in this series. At the moment, one Nepalese student is doing further research on this topic, and from what I hear, my notes are helping him, but I wouldn't expect any other answer, so I really hope that they're helping him. Uh, yes, and on the bottom part of the slide shows the actual challenges that I have encountered in this thesis, and the primary one in the beginning of the thesis was to read previous bachelor thesis. The problem with most technical bachelor theses, and I guess all bachelor theses in general, is that nobody is expected to read them afterwards. And it's pretty dense reading because, well, sadly, bachelor level students are not professional writers. And I can say the same about myself, so it was quite a challenge there. And yes, as you have seen, the realistic model and results of Geraldo included 10 different test series and with different weld sizes, and I had to choose which one was the most appropriate one. In the end, I have on my personal drive about 1 gigabyte of photos made of his specimens, measured and analyzed. But I ended up choosing the simplest one, which was a fillet weld with throat thickness of 6 millimeters. But that's not that important, really. And modeling in LS-DYNA was quite an interesting process because LS-DYNA is a great tool for analysis of pretty much any physical phenomena, but at the same time, since it gives you so much freedom, you also have to know what you're doing. And to find out what you're doing, there are two manuals, 1,000 pages each, explaining all of the functions that program can provide to you. Hopefully, I had a guidance of a professional LS-DYNA user, so I didn't struggle with it as much as I could have. Okay, yes, and LS-DYNA had a really complicated problem with itself, which was the license of it. It's fairly annoying to deal with such problems because as a structure engineer, I had no idea how to fix that and relied entirely on the help desk of HAMK, who didn't know how to deal with it at first because very few people use this program, but we managed to get through it eventually. It was quite a long process, which required me to send a lot of letters. But I guess that's what life is. And then comparison of the model and the experiment results. So on the left, you can see the picture of the specimens I have chose in the tested shape already. So you can see the fault lines and basic deformations, which I have followed as one of verification points of my model. And on the right, you can see one of my first models. Initially, I was testing the specimens as a whole. So the height of one plate is 200 millimeters, and so the width of the bottom one is also 200 millimeters. And the thickness in the perpendicular direction is 8 millimeters in each one of them. So that was the initial data. And this was a final model. I ended up cutting most of the model away, leaving some simple support conditions. I have decreased the shell element. I have decreased the element size. So initial element size was 2 millimeters. And I have shortened the model to actually focus on the critical part of it because the rest of it didn't really matter due to, well, similar material properties. You can ask questions about it later because there are quite a lot of details with those things. So from this moment on, there will be 7 slides showing the failure progression of my best model. As you can see there are two parts of it, which is von Mises stress, which shows the actual stress resultant in each shell. The numbers are a bit weird there, but basically when you see 9.74, it actually means you should multiply it by 100 to get megapascals. And that's one of the things with LS-DYNA is it doesn't have units of measurements choice. You have to define the relation of units by yourself and then to evaluate it yourself as well. So if some mistakes have been made in definition of material properties, it can make results unusable from a mathematical point of view. So you cannot really compare it to anything else. And on the right, it shows effective plastic strain, which actually I included here. Usually it's not included in such thesis presentations, but I enjoyed it and I find it more usable because it shows the propagation of a fault line. As you see, when it stops being blue, it means that some plastic elongation has happened at the shell. And when a limit of plastic elongation is reached, a shell is deleted and the movement can continue further. And so the more shells are deleted in critical zone, the more stress concentration happens there. So that's something to look after. And also at the bottom of the slide, there is a number. Like in this slide, it's 291 out of 2011. It shows from which clip of animation it is. So it's a sort of measurement of time, but not directly. And at the top of it, it mentions the vertical displacement of the top nodes where the load is applied. At this point, it's 0.29 millimeters. It is relevant because when I compare my modeled results to experimental results of Giralda, displacement is a big part of it. So at each slide, I'm going to give you about 10 seconds to look at it and try to understand the process. So here we go. So, and as you see, this was the final condition, the final state of failure of this model. And if we go back to the failure, to the actual specimen, you can see that failure is about similar. It's the difference is that my heat affected zone is linearly distributed as just going underneath the weld, but in reality it's more of an arc shaped. But I decided not to over complicate the calculation model for that case, because the area of stress distribution is about the same, even though it would probably increase the resistance of the model. So this was the results that I got in kilonewtons, and the displacement, as you can see, at 1.8 millimeters of displacement, it fails completely, but the actual failure starts at about 0.8 millimeters. Such a small displacement is a result of very strict boundary conditions, the support conditions, restricting any movement in the bottom plate of the welded assembly. And the failure load is about 48 kilonewtons in the model. And now for the experimental results. Experimental results shows that the failure happened at 70 kilonewtons and a displacement of 14 millimeters. But this displacement cannot be trusted because the test assembly was it allowed quite a lot of movements and had other imperfections. But this is what next slide shows about it. So all in all, I'm quite proud of the work which I did, even though the final results are not exactly as they should have been. Though considering the number of imperfections and uncertainties included in the initial analysis, which includes that the test results of Giraldo cannot be truly verified because the test arrangement was imperfect, but that's already been dealt with in the process of my thesis by another bachelor thesis, which was finished after I was done by Mr. Antimonic. You can Google it on Tezels if you're interested in such a thing. So the next test in this series will probably be better. Or so I hope. And also the heat affected zone properties are a very varied topic. So the final model uses the model of heat affected zone to be to have 90% of strength of parent material, which is a model suggested by Eurocodes for calculation of such things. But it is not entirely true as I understand it, because it still doesn't, my model doesn't show differences in heat affected zone formation in high strength steel compared to normal carbon steel, because I suppose that 90% is more about the carbon steel thing. So, and practical application and labor market links, it was written 10 minutes before my final presentation 1 year ago, so it's, well, it's not really content field. But I guess all of those things are true if you think hard enough about them. And I think it's question time. As Confucius once said, wind is basically air. So if you have any questions, I'm ready to explain them down to the basic concept as far as I understand them. Thank you for your time.
Thank you, Philip. We have time for questions, so please be active. You can use the chat. I will follow it. I have one question. Now it's been 1 year since you did this thesis. Would you change something now? And has it been beneficial in your work?
Yes, I'll start with the last question. It is beneficial in my work, even though it is not directly connected to it, because nobody will use LS-DYNA in practical analysis because it takes so much time and the margin for error is so high. But it helped me to gain confidence in dealing with engineering topics which I don't initially understand and which I cannot understand without sufficient practice. So that is the main benefit, really, is that I can talk about it with confidence and that I can deal with supposedly simpler matters. And would I change anything? Yes, I think I would. I would make it, if not better, but better outline, better presented. As my thesis initial draft of my thesis almost reached 100 pages, it had to be cut down to 60 because 100 pages of, well, it was basically my ramblings about how things are wrong and how I'm trying to estimate the uncertainties of initial data that I had and how many assumptions I made and how I made them. So I think I would do better, but I don't know by how, by what margin really.
Thank you. We have another question uh, from Bacha. Do you think we can refine the results by using, let's say, Abacus, etc.? If you think there were any limitations to LS Duna. I'm sorry if I pronounced it
Oh no, 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 no,
wrong.
nobody knows how to pronounce it, so I guess all pronunciations are correct. Uh, I think it can be refined, maybe not by mathematical core of calculation of the program, but by user friendliness of the interface. For example, LSDyna, I worked like it is used by the mathematical core, with the calculation core of this program is used by ANSYS program, which is somewhat similar to Abacus in the same class. But Abacus modeling tools are much better than original LSDyna tools. However, LSDyna modeling tools and then animation tools are free to use, while for both Abacus and ANSYS you have to pay quite a solid licensing fee for modeling interfaces as well. But I think it can be improved just by the nature of easier data management of the model, like material properties and all that. In case of pure LSDyna, it's quite, well, it requires a lot of windows open, a lot of windows closed, and you have to remember where you put what. And since it doesn't allow you to set units just by choosing millimeters or centimeters, or just choosing a global system of measurement, you have to double check yourself a lot. While in things like Abacus and ANSYS, it's not the case. It's easier to apply loads and all of the data for the calculation, and then to check this data.